All right, so I think we are going to get started. We are going to check chapter 14 today, but first reminder will be Hulk number one is due tomorrow, okay, by midnight. Um, Many of you guys actually have finished this one already, and some of you guys are almost done. But I still see there's just a couple of you guys haven't actually signed up, okay, for the expert here. So make sure uh, you get started. Okay, it's due tomorrow. And as I think you guys got the email from Kayla. So she's still doing the tutoring as well as SI section for this class. The SI sections are on Tuesday, 10:20. Okay, here you need to sign up. If nobody signs up, she will not show up here. Okay, but that's extra help you can get. All right. So and then for in-seat classroom disinfection today, Austin and Jared. Okay, so after the class, please do that for us. All right. So in this chapter, we are going to take a look on heat and the transfer of heat. Okay, so heat. This is a concept in physics. It's defined as the so if you have two objects in contact, for example, if you have a can of soda and then if you place it into ice, all right, so then the soda will cool off. So that's heat transfer from the soda to the ice. Okay, so the spontaneous transfer of energy due to temperature change difference is called heat. Okay, so when you have two objects that are in different temperature, you bring them in contact, there will be transfer of heat from the higher temperature of object to lower temperature of the object. Okay, so that amount of energy is called heat. All right, so in this class, we are going to use Q, symbol Q, capital Q here. Um, now, you can see like lower Q in other textbooks, so but it's basically just a symbol, okay? It doesn't really mean a lot of stuff, but we'll use Q here. And because heat is the form of energy, so it has the same SI unit of energy as joule, all right? Um, Other units you might be seeing like calories, right? I think you hear a lot about this in like in the food you are eating, how many calories there. So 1 calorie is equal to 4.186 of joules. Okay, that's the conversion factor. If you see um, capital C as calorie, then that means actually means kilocal. Okay, so maybe paying attention to that a little bit, but you'll be given conversion factors here. If you are solving a problem, you can either look it up or in the exam, you'll be given the converting factor, okay? Um, so for 1 calorie, it's actually defined, I think it's on the previous slide. This is defined as if you change the temperature of 1 gram of water by 1 degree Celsius, the energy needed, okay, to do that, or the heat needed to do that, it's called 1 calorie. Okay, so that's equivalent to 4.186 joules. And then that's based on the experiment that James Joule conducted a couple hundred years back. So where he had this set up. Okay, so you have like two weights, known weights, you know the masses, and then they are connect to a string over here at the two ends here. The string is wrapped on this cylinder over here. And if you let go of the two weights, all right, you'll see then the potential energy here will be converted into kinetic energy. We'll make this rod moving, so then it will stir the water here inside here. So water here is isolated, okay, or insulated. So then you can monitor the temperature change of that. Okay, so he found out that if you do this, then the temperature here will increase. Okay, so that means you are converting the gravitational potential energy into the heat that needed to increase the temperature of water. Okay, and um, he found out that 1 joule, or actually in order to increase 1 degree of temperature here, you need 4.186 joules of energy, okay? And then due to his contribution to the field, then energy is given the SI unit after his name joule, okay? So, but this experiment demonstrated the equivalent of heat and then energy, okay? So heat is a form of energy. All right. Now, as I mentioned, if you put heat or if there's heat change of the object, then the temperature of object will change, right? So this can be expressed by this equation here. So Q is it's the heat added to the object or the system. If you have say a few objects in the system, then that equals to mass times C, which is a constant number. Okay, this is the mass of the object times the constant number here times delta T. And it turns out this constant number C, all right, it's this called specific heat capacity of the substance. So it's the one of the property, intrinsic property of substance. For example, water has its specific heat capacity, all right? And then metal, like iron, has its own, copper has its own. So if you can determine the specific heat of the material, then you can look up in the table to find what material this is, okay? So this is the substance dependent coefficient there, okay? So Q equals to M times T sine delta T. All right, so for the C here, as I say, it's called specific heat, or sometimes referred as specific heat capacity, okay? So these two terms are interchangeable. All right, it has a units of joules over kilograms times K, or joules over kilograms times degrees Celsius. Okay, so because for Kelvin and Celsius, they are the same scale if you are talking about the temperature difference. So these two are the same unit here. Okay. All right. Sometimes you see specific heat unit as kilokelvin times divided by kilogram degrees Celsius. So you can see there's also like other units can be used here for specific heat capacity. So you want to pay attention to the units, okay? Many times you have to do conversion if it's not given in SI unit, but this is the SI unit, okay? All right, let me see. So maybe not in the PowerPoint slide, but sometimes you see people write this equation as, bring this out over here. So sometimes people write the equation as Q equals to capital C times delta T, all right? The one you're seeing on the slides is Q equal to the mass times small c times delta T, all right? So in that case, if you see an expression like this, capital C, so that means capital C equal to mass times small c, okay? So then this is called the heat capacity, all right? In this case, this is called specific heat capacity, okay? So the relationship between these two is small c should be equal to capital C divided by mass. So that's capacity, heat capacity per kilogram. Okay, so specific capacity means heat capacity per kilogram or unit mass. Okay, so that's there. So just in case if you see a different expression like that, that means it's just heat capacity. Okay, and then this is heat capacity per kilogram. All right. Okay. All right. So as I mentioned, the heat specific capacity is substance dependent. Okay. So you can actually look it up on this table for given substance. Okay. So one thing you might want to pay special attention is water. Okay. Specific heat capacity for water is 4186 joules per kilogram per degree Celsius. Okay, or 1 kilocalorie. Okay, so that gives you pretty much gives you the conversion between the two units there. And if you look at the rest on the table here, you'll find water has the maximum heat capacity. Okay, than the rest of the materials. Okay. Now human body is made like most part of our body is water. Okay, so that's why it's very close to water. So 3500. Okay. Ice, the other format of water is 2090. Okay, so this is solid form. Okay, it has smaller. In general, liquid will have more heat capacity than solid. Okay, so for example, water is this guy, and then ice is that guy. Okay, and then for other substance as well. Metals, so you can see metals like aluminum, copper, gold, etc. Silver, lead here, they are having relatively less heat capacity. Okay, so that means they can heat up very quickly. So like your cooking pans, they are pretty much made of iron. So that's the reason there. Okay, and then like the coolant in your car is pretty much water. That's because it has a very large heat capacity. Okay, so that can keep the your engine cool. Okay, not to temperature of it not to go up significantly. All right. Now the big application of heat capacity is you can actually calculate what's the heat transfer between two objects if you put them in contact. Okay, and in chemistry you do this a lot by doing calorimetry. Okay, so one way of if you want to identify a substance is doing to measure its heat capacity. If you can identify it, then you can pretty much identify the material itself. Okay, so this is what a heat calorimeter does. Okay, so this is a device that is very lightweighted. Okay, and then it's pretty much very well insulated. Okay, container that contains water, and when an object is put in, the water and the object will come to a thermal equilibrium after some time. Okay, so then you can measure the mass of the object, and then you can calculate, you can measure the final temperature and the initial temperatures. All right, and then you can calculate and then to find out the heat capacity from there. Okay, so this is what a calorimeter does. All right. So the final temperature of the object and water will be equal to each other. Now, during the process, the whole device is very well insulated, so you can assume there's no heat exchange of the system, the water and the object, with the outside surroundings. Okay, so then you can apply total energy of the system is conserved. So basically, you will apply that the heat transfer from water to the object is equal to that the heat that is taken out, or that heat is added to the object. Okay, so in that sense, so that means water will lose either way. If the temperature of water initially is higher than the object, then water will lose heat. Okay, and then the object will receive heat. On the other hand, if the initial temperature of water is cooler than the object, then the water will receive heat. The object will lose heat. Okay, so the object that one receives should be the heat one receives should be equal to the heat that the other one loses. Okay, so that's the energy conservation here. All right. So we are going to take a look on one example to see how you can actually do that. And you guys are going to have a lab on this next week, I think. If not, then it will be the week after. Okay. All right. So let's take a look on this example here. This one says a 225 grams of lead ball at temperature of 81.2 degrees Celsius it's placed in a light calorimeter containing 155 grams of water, initially at just 20.3 degrees Celsius. In this case, you are given the heat capacity of the lead, okay? So you can actually calculate, predict what's the final equilibrium temperature of the system, okay? And in some cases, I think will have a problem in the homework assignment that you are given just the final temperature of the system, and then you will be looking for what's the specific heat of the object. But it's about the same procedure you will have to be doing to solve the problem. Okay, so in this one, you are not exactly looking for the specific heat capacity that you can predict what's the final temperature. Okay, let me see. All right, I'm going to stop sharing. So for you guys are online, you can pull up the PowerPoint slide on your end. So we'll list the knowns given by the problem here first, okay? So you are given that the initial temperature of the lead, okay, I'm going to just use the chemical symbol of lead, Pb, for that. So T of Pb initially, that's 81.2 degrees Celsius, okay? And then T of water, initial is 20.3 degrees Celsius, okay? It tells us that specific heat capacity for the lead is 128 joules kilograms degrees Celsius. Specific heat capacity of water is equal to 4186, I think. For some reason, my note says 4185, but it's given 4186 here. All right. We have a double check on this. Looks like it's given in kilograms times Kelvin, but kilogram times Kelvin is equivalent to kilogram times degrees Celsius. Okay, so I put degrees Celsius here for that reason, because joules per kilogram times degrees Celsius, that's equivalent to joules per kilogram times Kelvin. Okay, they are the same. All right. Now we also know the mass of the two, the metal and the water. So this is 225 grams. The mass of water is 155 grams. Okay. You are looking for what's the final temperature, T final, of the two when they are placed in contact. Okay. So the key concept here is energy conservation. Okay, so that means the energy received by the water is equal to the energy that gives out by the metal. Okay, so let's see. For metal, delta Q PB, okay, that's equal to, or you can just say Q. Let's just say Q, okay. Q, that means the heat changes is equal to mass of it divided times specific heat capacity times delta T, right, of it, PB. The same thing you can write the Q for water, the heat change for water should be equal to its mass times specific heat capacity times its temperature change, okay? So temperature change of water, all right? So then this is equal to MPB, CPB, change in temperature will be T final minus T initial of it, right? Similarly on this, on the water here should be M water, C water times T final minus T water, right? So this is heat change for the metal. This is heat change for the water. Okay. So then for energy conservation over here, you should have the two add up to be 0, right? Because one will receive heat, one will lose heat, or this one loses heat, and this one receives heat, okay? So then the change, for example, if this one loses 5 joules of energy, then the change of the heat should be -5, right? Because it loses heat, that means minus. And then this one should receive positive 5 joules, right? So then the two add up should be equal to 0, okay? So this equation is the energy conservation. All right. Okay, so then basically you're going to do this one plus this one that goes to 0. So then you will be doing MPB, CPB, TF minus TPB plus M water, C water, TF minus T water. That goes to 0, okay? When you set this up, then you'll find that in this equation, so the only unknown will be the T final. You have two T finals, okay? So T final there. And then the rest of the quantities, they are given, they are all given. So then you can solve for your T final, okay? So this is the basic equation starting from here. Now, as I mentioned, you might be given in a problem that the final temperature, but then you are looking for, say, the specific heat capacity of the metal, okay? So then in that case, then the unknown becomes this guy, right? In that case, this is the unknown, and then the rest, they are known, okay? So then again, you can solve for that see the specific heat capacity of the metal, okay? But in this problem, let's just take a look on how to solve the T final here as an unknown, okay? All right, so you are going to expand the parenthesis here, like distribute this into the parenthesis there, and then also this two into the parenthesis there, okay? So you will end up with MPB CPB times T final minus MPB CPB times TPB, okay? That's distributing the two quantities into a parenthesis. Now plus MH2O CH2O TF minus MH2O CH2O TH2O. That goes to 0, okay? You're looking for TF, so there's TF here, there's TF here. Now you're going to combine those two together, okay? And then you can move the rest to the other side of the equation, all right? So adding these two up, you'll get MPB CPB TF plus MH2O CH2O TF, right? And then equals to, you move those two terms to the other side equation. The negative sign becomes positive. So MPB CPB TPB plus MH2O CH2O TH2O, okay, on the other side of the equation. You're solving for TF, so you want to single out TF, right? So TF is the common factor on these two terms, so you can single out TF that way. MPB CPB plus MH2O CH2O, okay, times TF. That goes to equal to the other side of the equation. All right. Then TF should be equal to the other side of the equation, MPB CPB TPB plus MH2O CH2O TH2O divided by MPB CPB plus MH2O, CH2O. Okay, so this is just algebra. Okay, so after you have come up to the final expression for TF, then you can plug in your numbers. Okay, because all are given as knowns on the right hand side equation. Okay, so then you can take the numbers in there. TF then equals to MPB is 225 grams. Okay, CPB is 128. Okay, TPB is 802 or 81.2 degrees Celsius. Okay, plus MH2O 150, 4186 joules Kelvin degrees Celsius. T 20.3. Okay, that's what you have on the top. Divided by what you have on at the bottom here should be 255, 25, 128 plus 155 times 4186. Okay. Then your final answer is going to be 22.9 degrees Celsius. Okay. Now in here, I didn't convert grams to kilogram, okay, because there's gram here, gram here, gram here, gram here, okay. If you have on each of the terms here as grams, then you don't necessarily have to convert into kilogram. You could do that, that's fine, okay. It will not change your result. Basically, you're going to multiply by 10 to the -3 for each of the terms, right? On the top and then on the bottom, so they will cancel out anyway, okay? So you don't have to do that because of that, okay? And then in this case, you can stick with degrees Celsius, not converting them into kelvins. That's because you are starting with these two equations, okay? You are looking at the change in the temperatures, right? Both here and there. So change in temperature in Kelvin and then change in temperature in Celsius, they are the same, right? So that's why you don't have to change convert it to given temperature into Kelvin because you'll be doing change in temperatures, right? As I mentioned earlier, change in temperature in Kelvin and in degrees Celsius, they are the same, right? They are the same scale, okay? So that's why you don't have to. You could convert them into kelvins. Then at the end, you'll get the answer in kelvins, okay? Then you can convert that temperature back into degrees Celsius if that's the unit asked, okay? If not, you can keep that Kelvin temperature, that's fine, all right? So just something I want to mention about why I didn't do the conversion of the two units here, okay? Any questions you guys might have? So we can capture this. All right. That's almost the whole picture. All right. Okay, so if you are clear on this one, I think we can move on. Okay, so next we are going to look at phase change and latent heat. Okay, so as we know, like you can have different phases for the same substance. For water, you can have like solid water, which is ice. You can have liquid water, which is water, and then you can have like steam, the vapor form of it. Okay, so um, when you are having phase transition, okay, you probably will realize, or you might have learned this in chemistry, like if you have ice, okay, you'll increase the temperature of ice, so then it can go from say -20 if you start from -20 degrees Celsius, which is below the freezing temperature of 0 degrees Celsius. Okay, you can raise the, you can add heat to it. You can kind of like heat it, then it will not melt as long as the temperature is not 0 yet. Okay, and then when it's at 0, you'll see that if you keep heating it, if you monitor its temperature, before it's fully melted, you temperature of it will keep at 0, will not change. Okay, so in that case, you are adding heat to the system, but the temperature of the system is not changed. Okay, so then that's the one of the special case when we mentioned earlier for the heat capacity, we say you will add heat to the object, then the object temperature will increase, right? But in this case, that's not true. Okay, so when you are having phase change, then the heat you added to just is responsible for the phase change here. Okay, so the amount of heat that is needed to add it to say 1 gram of the substance in order for it to complete, say, melt. Okay, so it's called the latent heat of the melting process. Okay, so then the heat needed for 1 kilogram of ice to fully melt, that's called latent heat of the ice melt. Okay, and then after that you can keep adding heat to the water, and then the temperature of water will increase until it reaches 100 degrees Celsius at 1 atmosphere pressure, which the water at that point boils. Okay. Now, if you monitor the temperature of the system, you will see that at that point, if you keep adding heat to the system, the temperature of the system will not change. It will keep it will keep at 100 degrees Celsius, okay, until all the water is converted into vapor or steam. Then after that point, if you add more heat, and temperature of the system will increase again, okay. So for this process, the vaporization process, then the heat needed for all the water to vaporize is called, again, latent heat of vaporization in that case, okay. So during the phase transition, um, the heat, if you add heat to the system, the temperature will not change, okay? But rather it's changing the phase of the substance, okay? All right, so that's phase change and latent heat. For latent heat, again, it's heat, so you can say Q equals to M times L, okay? So in this case, you don't have change of temperature, so there's no term of change of temperature, it's just mass times latent heat. We use symbol L. For latent heat is joules per kilogram, okay? Now you could have different process, you could have melting process, or you could have vaporization process. So latent heat for different process. If it's melting, you use L sub F, which F stands for fusion, okay, process. And then for vaporization is L sub V, V stands for vaporization. Now, on the other way around, if you have water that is freezing, okay, then you need to take the same amount of heat out of the process per kilogram of water, okay? So LF is referring to both melting and freezing. When you are melting, say 1 kilogram of water of ice, say if you need 2000 joules of energy, then in the reverse process, if you want to freeze 1 kilogram of water into ice, you need to take out also 2000 joules of energy. Okay, so that's the same amount. Okay, similarly for vaporization and condensation process, the reverse process, you need to take out the same amount of heat, okay, as you would have to vaporize it. Okay, all right. Again, for latent heat, is specific to substance. Okay, so for again, you might want to take a look at the water here. For melting of water, it happens at 0 degrees Celsius. The amount needed is 334. This is in kilojoules of per kilogram. So over here, you can take a look. This is kilojoules per kilogram. So 334,000 joules. Okay, it's a lot of energy. All right. And then for boiling, when it happens, you have vaporization. You need even more energy for vaporization. So 222, 2,256,000 joules of energy. Okay. And then for the other substance, you can look them up over here as well. Okay. At what temperature that process happens, and then the energy needed in kilojoules per kilogram or kilocarbons per kilogram. Okay, and then for the vaporization process here as well. Okay, you can look up the numbers there. All right, I think you guys know this. If you would be hurt by steam, then compared to hurt just by water, right? It's going to be more severe that if you are hurt by steam, because if you are hurt by steam, that means because steam would have more energy, right? There, because you added more energy into water to become steam. Okay, so that's why, because it's added a lot of more energy or heat into it. Okay, all right. Now, fundamentally or microscopically, if you go from say solid to liquid, okay, so you need to add heat here, because for solid it's more like confined structure than liquid, right? Liquid has more loose structure. So that means you have to break out some bondings, right? So you need to add energy to break out some bondings here to make substance go from solid to liquid, okay? So in this process, to melt something, you need to add heat, okay? On the other way around, you have to take out some heat to become more confined structure. So then in the reverse process, you can take out heat. Okay. Similarly, going from liquid to gas, gas is even more disordered than liquid. Okay. So you need to take out energy to break out, or you need to add energy to break out some of the bondings here to become gas. Okay. And then the reverse process, you can release some energy, so it becomes more confined structure there. All right. We are going to take a look on an example on this. Okay, so this one says if you have 1.1 kilogram blocks of ice initially at the temperature of -5 degrees Celsius, if 5.2 times 10 to the fifth joules of heat are added to the ice, what's the final temperature of the system? Okay, I think I can give you guys a couple minutes for you to come up with a plan, or maybe think about how you want to solve for this, and then we would be looking at the solution together in a couple of minutes. Okay. All right, so I'm going to stop sharing my screen here, but look at a solution on the paper here, okay? So I think it would be easy if the problem involved here, if you don't consider phase transition, right? Then you simply say Q is equal to MC delta T, right? So if that's the case, then you can solve for delta T by given mass and heat capacity, right? And then the added heat. And then you can solve for final temperature. But reality here is this is ice, which is initially at -5 degrees Celsius, all right, which is very close to its melting temperature of 0, right? So if this is temperature here, degrees Celsius, if this axis is the heat added, all right, so then you'll see that as you increase the heat, then temperature will increase for the ice, right? Then when it reaches 0 degree here, it will melt, right? In that case, then the temperature will not increase, will stay the same, okay? And then after that, if the heat you added is enough, then it will become fully, at this point, become, the whole ice will become water, okay, totally. And then if there's the remaining heat to be added, the temperature of water will rise, again, okay? And if you have a lot of heat that is enough to bring it to boiling, then you might be reach the boiling temperature of 100 degrees, right? And then it will vaporize. And then if that's assuming you have so much heat, so added to the system, so then it fully become steam, and temperature for the steam will rise, okay? Now the question is, where do we stop? Okay, so given the heat that is added to the system, where do we stop? Do we stop at here somewhere? Do we stop here somewhere? Or do we stop here somewhere? Or here, or here, okay? So then the question is, where is your final stage? Okay, could be all this, right? These possibilities, 1, 2, 3, 4, 5. Okay, so it's complicated because there might be phase transition happening, okay? So then we will take a look, say, for this process, for the ice to temperature to increase from -5 to 0 degree, what amount of heat is needed? So I'm going to call this as Q1, okay? So then in this case, from here to here, you don't have phase transition, so then Q1 could be easily calculated. Q1 then is equal to MC delta T1. Okay, let me say delta T1. So for this process, okay, you can calculate that, see how much heat is needed. The mass is given as 1.1 kilogram times the heat capacity. So in this case, you would use heat capacity of ice, right? Because at below 0, temperature below 0 degrees Celsius, you have it still in solid form ice, okay? So for ice, it's given as specific heat capacity of 2090, okay? So times 2090 joules per kilogram degrees Celsius. Delta T1 from -5 to 0, so 0 minus -5 degree, okay? So then that's 5 degrees. So your Q1 is equal to, you can calculate this, going to be 11495 joules, all right? Or approximately 1.15 times 10 to the 4th joules, okay? So this is how much heat is needed to raise the temperature of ice from -5 to 0 degrees, okay? Now, the heat given to the ice, the total heat, okay, Q total is given as 5.2 times 10 to the 5th joules, right? So for the first part of raising temperature of ice from -5 to 0 degree, you are not using up all the heat that is added to the system, right? This is less than Q total, okay? All right. So now let's take a look on after the temperature of ice reaches 0, right? So that means you are having melting process now. So let's see how much heat is needed during this melting process. I'm going to call this Q2, okay? How much Q2 is needed? So you can calculate Q2. For melting process, you'll be doing like mass times just the fusion process, latent heat of the fusion process, right? The melting process. So you can calculate that 1.1 kilogram times for the melting process. The latent heat of ice melt is given as 335. Remember, it's given as kilojoules, so times 10 to the third joules per kilogram, okay? And then you can see this is going to be equal to about 3.69 times 10 to the fifth joules, okay? So at this point, we need to see if Q1 plus Q2 is equal or less than, or is greater or less than the total heat you added. Okay, so we'll compare, we'll have to do like Q1 plus Q2 to add up the first two processes to see what's the total Q. 1.15 times 10 to the fourth joules plus 3.69 times 10 to the fifth joules. In this case, this is 3.8 times 10 to the fifth joules, okay? So this is still less than the total heat you added, okay? So still less than Q total. So that means now your ice is fully melted, it becomes water. That's now still remaining heated to be added to the system, right? So the temperature of water will raise, okay? At this point, you can take a assumption that because you probably can, or maybe if not, but if you know that from here to here, it probably need a lot of energy, right? From 0 degree to 100 degrees. So I'm going to assume that now it's not going to be 100 degree here, right? So I'm going to just say for this is my Q3, okay? For the Q needed here to reach my final. So Q3 then will be equal to the total Q minus Q1 plus Q2, right? That's Q3, right? Because that's the excess heat after these first two processes, right? So this would be equal to 5.2 times 10 to the fifth joules minus 3.8 times 10 to the fifth. That's equal to 1.40 times 10 to the fifth joules, okay? So this is my remaining heat to be added to the water. I'm going to assume now it's not reaching the boiling temperature of 100 degrees Celsius. I'm going to calculate what's that final temperature, right? Because that final temperature should be equal to the mass of the water times specific heat capacity of the water this time. Okay, so remember here you should use the value for water because now it's in the liquid status times delta T. All right. And then in this case, delta T3 here. So delta T3 should be equal to my final temperature minus 0 degrees Celsius, right? It starts from 0, reaches to the T final there. Okay, so I can calculate what's the so this is basically T final. So then T final should be equal to my Q3 divided by mass times CH2O. Okay, so I'm going to see what's that number. 1.1 kilogram for the mass. Ice melted to be water, the mass still remains, right? You have 1 kilogram of ice will melt into 1 kilogram of water, right? Times 4186 joules per kilogram per degree Celsius. All right. So it turns out this is going to be about 30.4 degrees Celsius. All right. This is indeed less than 100 degrees Celsius, right? So my assumption was correct, okay? So then you can keep that as your final answer, okay? Now, it may turn out that this is bigger than 100 degrees, say 120 degrees, okay? So that means your assumption was not right, okay? So then this is not the final answer then, okay? So in that case, if it turns out to be more than 100 degrees Celsius, then your water will become, will reach the temperature of boiling, all right? Then you have to calculate what's that Q3, okay? And then because you have more than 100 degrees, that means it's at least going through the partially vaporization process, okay? So you want to find out what's the total Q needed here for the fully vaporization. Then you add Q1, Q2, Q3, Q4 up and compare to the total Q, okay, in that case. But I don't think you are probably not going to see a problem like that, okay? But it's the same logic behind, okay? You can actually do it that way, okay? So here is the how you would work on a problem like this when you have phase transition involved, okay? All right. Any questions you guys might have? Okay. So if not, there's just like 3 minutes remaining. So I think I'm going to stop here. But again, I would like to remind you guys, homework number 1 is due tomorrow, okay, by midnight, right? And then if you are in the lab this afternoon, I will see you in the lab, okay?
Thank you.
You're welcome.